Okay, hello and welcome back. In this video, we're moving on to section 9.6. So we've been discussing vectors on a two-dimensional plane, just on the xy plane. So we're going to extend that into three-dimensional space, where we have a third axis, often called the z-axis. So just to orient ourselves, it's kind of difficult to draw a three-dimensional axis on a two-dimensional sheet. We're reducing a third dimension into the second dimension. But when drawing a three-dimensional axis, we take this line as our x-axis. So this is the positive x direction. We take this line as our y-axis. So the positive y's are on this side. And then the vertical axis is our z-axis, x, y, z. So a way to remember this orientation is through something called the right-handed rule, which they have a diagram here. If you take your right hand and put it into this position, your pointer finger will point in the direction of the positive x-axis. Your other fingers will curl in the direction of the positive y-axis. And your thumb will go in the direction of the positive z-axis. So this is called the right-hand rule. So far we've been plotting points and doing work on the two-dimensional xy plane. So we would call a point x comma y. Well, a point in the third dimension just has another input. You have some x value, some y value, and some z value. So there's an example of plotting some points in 3 dimensions. We form this three-dimensional box. So for example, this point here, 2, 3, 0, you would go a distance of 2 in the positive direction, x direction, then a distance of 3 in the positive y direction, and no distance in the z direction. Well, this point up here, 2, 3, 4, we would go first to our previous point, and then up 4 units in the positive z direction. You get our coordinate point. So it's a little bit tricky writing this on paper. These days we have all kinds of visualization software and tools to view things in 3 dimensions. So it becomes less of an issue. But we can use the right hand rule if we're looking at some diagram like this, or if we had to produce it on paper to orient where our axes should be. So we'll be doing our work with vectors in the third dimension. So we'll redefine a lot of the properties, and we'll see this will ultimately just add an extra term, like how in a coordinate point in the third direction, we get an extra term here for our z position. But we start out just finding the distance between 2 points in space in the third dimension. So if we recall on the xy plane, the distance between 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared. It's actually just another expression of the Pythagorean theorem. So if we're in the third direction, if we have points now, if point 1 is x1, y1, z1, and point 2 is x2, y2, z2, the distance formula looks pretty much the same. We just have this term for our z variables, or our z coordinates, I mean. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And that's all under a big square root. So let's find this distance between 2 points. Point 1 in example 1 is negative 1, 3, 2. And point 2 is 4, negative 2, 5. So our distance between these 2 points, it'll be under a big square root. So we'll have the difference of our x values squared, so 4 minus negative 1 squared, plus difference of our y value squared, negative 2 minus 3. squared plus the difference of our z value squared, 5 minus 2 squared. So that should be 4 minus negative 1 is 5, so 5 squared plus negative 2 minus 3 squared, that will be negative 5 squared, plus 5 minus 2 squared, 5 minus 2 is 3, so 3 squared. So that would be the square root of 25 plus another 25 plus 9, which will be the square root of 59. So distance between 2 points in the third dimension looks very similar to our regular distance formula in 2 dimensions, but plus a third term, the z2 minus z1 squared. So with this in mind, let's use this to find a position vector in 3-dimensional space. So we can describe a 3D vector in component form as A, B, and then we'll have some additional input value C in the third dimension. Using unit vectors, we've seen I and J, and we typically use K as our third dimensional unit vector going in the Z direction. So I'll write that up here too. So we can say A, I plus B, J plus CK. So if you recall, to find a unit vector for a 2-dimensional vector, we had just difference of x values times I plus difference of y values times j. So we'll just have a difference of z values times k as our third term. So let's do that in example 2. We want to find the position vector if our initial point is negative 1, 2, 3, and our terminal point is 4, 6, 2. So our vector in component form should just be 4 minus negative 1, comma 6 minus 2, comma 2 minus 3. So that would give us 5, 4, negative 1. And in IJK form, that would be 5i plus 4j minus 1k. We can do all of our familiar operations with vectors in the third dimension as well, so we can add them together. Vectors are equivalent if they have equivalent components, if the a, b, and c values are the same. Vector addition is just the sum of related components. Vector subtraction is the subtraction of related components just with our extra term. Scalar multiplication, that scalar value multiplies to each respective component. And then the magnitude of our vector will be the square root of the sum of all 3 components instead of just a and b. So pretty much everything's the same. We just get an additional term that we deal with. And I'll just write this in component form as well, just to show. So vector v plus or minus vector w. I'll do plus or minus just to do 2 for 1 here. So this would be a1 plus or minus a2, comma b1 plus or minus b2, comma c1 plus or minus c2. And then scalar multiplication, that would be c times a1, c times b1, c times c1. Probably should use another another letter because of the double C's. I think that's why they typically use alpha here. All right, let's get some practice working with some of these operations. So we have vector v, can write that as 2, 3, negative 2. And vector w is 3, negative 4, positive 5. So let's find v plus w. We'll just add our components. So that will be 2 plus 3, which is 5, 3 minus 4, which is negative 1, and negative 2 plus 5, which will be positive 3. So that would be 5i minus 1j plus 3k. And then v minus w, that would be 2 minus 3, or negative 1. 3 minus negative 4, so 3 plus 4 is 7. And then negative 2 minus 5 is negative 7. So negative 1i plus 7j minus 7k. And we can do other combinations like we've done before. So with two vectors, v is 2, 3, negative 2. W is 3, negative 4, positive 5. So let's find 3 times v. So we would just distribute that to every term. That would be 6, 9, negative 3, or 6i plus 9j minus 3k. Oops, no, not minus 3. That should be minus 6. Because 3 times negative 2 give us minus 6 here. Part B wants us to find 2 times vector v minus 3 times vector w. So that's 2 times 2, 3, negative 2, minus 3 times 3, negative 4, 5. So let's scale these two vectors. The first one will give us 4, 6, negative 4. We can say minus 9, negative 12, 15. So let's do that subtraction. 4 minus 9 will give us negative 5. 6 minus 12, or 6 minus negative 12, that will give us 6 plus 12, so we'll get 18. And then negative 4 minus 15 will give us negative 19. So our vector would be negative 5i plus 18j minus 19k. And then part C asks us to find the magnitude of vector v. So that will be the square root of the square of their components added together. So that will be 2 squared plus 3 squared plus negative 2 squared. So that would be the square root of 4 plus 9 plus 4, or the square root of 17. So familiar operations, we just have this extra term for the third dimension. We can find the unit vector in the direction of v in the same way by taking the vector and multiplying by 1 over its magnitude. So if our vector v in example 5 is 2, negative 3, negative 6. Let's find its magnitude. Magnitude of v would be the square root of 2 squared plus negative 3 squared plus negative 6 squared. So that should be the square root of 4 plus 9 plus 36, which adds up to 49. So the square root of 49 is 7. So that means our unit vector in the direction of v should be 1 over the magnitude of v times the vector v. So that would be 1 over 7 times our vector 2, negative 3, negative 6. So everything will be divided by 7. So that would give us 2 over 7, negative 3 over 7, negative 6 over 7. Or we could say 2 over 7i minus 3 over 7, since it's negative j minus 6 over 7k. So we can find the unit vector in the same direction by dividing by its magnitude or multiplying by 1 over its magnitude. We can also find the dot product. So this follows also from our previous definition. If we have two vectors, the dot product of the vectors is the multiplication of their a terms plus the multiplication of their b terms, now plus the multiplication of their c terms. So let's find if v is 2, negative 3, 6, and w is 5, 3, negative 1. Let's find v dot w. That should be 2 times 5 plus negative 3 times positive 3 plus 6 times negative 1. So that would be 10 minus 9 minus 6. So that should be negative 5. Part B asks for w dot v, but remember we saw last time that the dot product is commutative. If we flip the order, we should get the same value. So feel free to work that out if you would like to prove it to yourself, but we would end up just flipping the order of this multiplication for each of those terms. We'll still get the same value in the end. Part C asks for v dot v. So that would be 2 times 2 plus negative 3 times negative 3 plus 6 times 6. 2 times 2 is 4, negative 3 times negative 3 is positive 9. 6 times 6 is 36. So that will give us 49. Part D asks for w dot w. So that would be 5 times 5 plus 3 times 3 plus negative 1 times negative 1. Or 25 plus 9 plus 1, which will give us 35. Part E wants to, oops, come back. Part E asks for the magnitude of v. Well, that should just be the square root of the dot product, because that would be the square root of 2 squared plus negative 3 squared plus 6 squared. Notice that was our same operation here. So we'll get the square root of 49, which is 7. And then f wants the magnitude of w. So using that same argument, that should be the square root of w dot w. So the square root of 35. So we get these same properties as last time, that the dot product is commutative. We can have a distributive property with the dot product in 3 dimensions. A vector dotted with itself is equal to the square of its magnitude, and if we dot the 0 vector with a vector, we get 0 as the result. We can also find the angle between 2 vectors in the 3rd dimension. We'll have the same formula. Let's recall that from last time. The cosine of the angle between 2 vectors is u dot v, so their dot product, divided by the magnitude of the first vector times the magnitude of the second vector. So for us, vector u is 2, negative 3, positive 6. Vector v is 2, positive 5, negative 1. So let's find their dot product. U dot v would be 2 times 2 plus negative 3 times 5 plus 6 times negative 1. So that looks like 4 minus 15 minus 6, which is equal to negative 17. Then let's find the magnitude of u. That will be the square root of 2 squared plus negative 3 squared plus 6 squared. So that will be the square root of 4 plus 9 plus 36, which is the square root of 49, which gives us 7. And then the magnitude of v will be the square root of 2 squared plus 5 squared plus negative 1 squared. So that will give us 4 plus 25 plus 1, or the square root of 30. So let's plug everything in. That means the cosine of theta should be equal to the dot product, which we said was negative 17, divided by the magnitude of u, which is 7, times the magnitude of v, which is the square root of 30. So that means our angle between vectors is the inverse cosine of everything on the right, which is approximately 116.3 degrees. So same formula, just working with 3-dimensional vectors. Now, the direction of the vector is described using 3 angles. So it's a little more complex than our single angle for the direction of a 2-dimensional vector. So we have our diagram showing the blue vector is the vector we're looking at. So this vector here in 3-dimensional space. So we can describe some angle coming from the positive x-axis to our vector. We'll call that alpha. We have also an angle coming from our positive y-axis, which we can call beta, and then the angle coming from our positive z-axis, which we'll call gamma. So we have these three angles that describe the direction of our vector. And they give us some formulas for calculating these. You can get these from mentioning some triangles. We can say that the cosine of alpha is the a component of our vector divided by its magnitude. The cosine of beta is the b component of the vector divided by its magnitude. And the cosine of gamma is the c component of the vector divided by its magnitude. So let's use that to find the direction angles for the vector in example 8. So they tell us our vector is -3 to -6. That's our a, b, and c term. We'll need to know the magnitude, so let's go ahead and find that. So the magnitude of vector v should be the square root of -3 squared plus 2 squared plus -6 squared. So that will be the square root of 9 plus 4 plus 36, which is the square root of 49 or +7. So we can say we want to find these three angles, alpha, beta, and gamma. So the cosine of alpha is the a component, which is -3 divided by the magnitude, -3/7. Take the inverse cosine and we get our alpha angle is approximately 115.4 degrees. Then the cosine of beta will be our b component, which is 2 divided by the magnitude. Take the inverse cosine and you should get that beta is approximately 73.4 degrees. Then we can say the cosine of gamma will be equal to the c component, which is -6 divided by 7 divided by the magnitude. So take the inverse cosine and we get that gamma is approximately 149.0 degrees. So we get our three directional angles using these three definitions. We get an additional theory called the property of the direction cosines. That the cosine squared of these three angles should be equal to +1. We're kind of reminiscent of our Pythagorean identity with sine squared plus cosine squared. So if we have cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma, they should all sum to +1. So let's say we're given two angles and we want to find the third one. That's where we can use this third property here, or this new property. So in example 9, they tell us that a vector v makes an angle of alpha being pi/3 with the positive x-axis. Beta is the angle of pi/3 with the positive y-axis. And there's some acute angle gamma with the positive z-axis. Well, so let's use this previous statement in order to solve for gamma. Because we can say cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma should equal 1. So that means we would have the cosine squared of pi over 3 plus the cosine squared of another pi over 3 plus cosine squared of gamma will equal 1. So we'll have two of those cosine squared pi over 3's. We can combine them together. We'll find out what that's equal to in a second. And let's subtract that over to the other side. So cosine squared of gamma will equal 1 minus 2 cosine squared of pi over 3. Well, the cosine of pi over 3 is 1/2. So that means cosine squared of gamma equals 1 minus 2 times 1/2 squared. 1/2 squared is 1 over 4. So 1 minus 2 times 1 over 4. So that means cosine squared of gamma would be 1 minus 2 divided by 4 is 1/2. So 1 minus positive 1/2 should give us 1/2. So let's take the square root of both sides. We would get plus or minus, so cosine of gamma is plus or minus the square root of 1/2. So the square root of 1/2, well, that's the square root of 1 over the square root of 2. The square root of 1 is 1, so we have 1 over root 2, which if we rationalize, we get our familiar root 2 over 2. But we're told that the angle is acute, so we must be in the first quadrant. Well, the angle in the first quadrant that has a cosine value of root 2 over 2 is pi over 4. So we can use this statement, this relationship between the squared cosines of all of our angles in order to find a third unknown angle if we do know two of them, and some information about the third. We were told that it was an acute angle. All right, and we can also write a vector in terms of its magnitude and direction cosines. So if our vector v is a, b, c, or ai plus b, j plus ck, we had said that the cosine of alpha was the a component divided by its magnitude, the magnitude of the vector. So we can solve for a and say that a is equal to magnitude of the vector times the cosine of alpha. We can get similar statements for b and c. So b would be the magnitude of the vector times the cosine of beta, and c would be the magnitude of the vector times the cosine of gamma. So that means we can write it as magnitude of v times cosine alpha I plus magnitude of v times cosine beta j plus magnitude of v times cosine gamma k. And we can factor out the magnitude since they all have that term. So that's what we have here as our definition. The magnitude of our vector times cosine of alpha I plus the cosine of beta j plus the cosine of gamma k. So we can write a vector in terms of its three direction cosines. Okay, so that's it for this section. Come back up here. So we found the distance between 2 points in three-dimensional space. Use that to be able to find the position vector in 3 dimensions. We did our operations, so addition, subtraction, scalar multiplication. We found the dot product in 3 dimensions, the angle between two vectors, and how to work with the direction angles. And mostly it was our same formulas, just with the third term for the third dimension. All right, that's it for this video, and I'll see you next time.